Hello everyone, welcome to the course of ultrasonic testing technology. The main content of this course is the drawing of ultrasonic testing curves. Through the study of this lesson, I hope to achieve the following teaching objectives. Master the significance and function of ultrasonic flaw detection curve. Master the classification and drawing methods of AVG curves. Master the classification and drawing method of distance amplitude curve. As we all know that a person's life cannot always be smooth sailing. It is like a winding curve. There are peaks and troughs. Peaks indicate success in career, happy events come. Troughs means difficulties, and so on. But as long as we won't forget our original intention and forge ahead, we will eventually reach the other side of victory and achieve the better life. Similarly, in the process of industrial ultrasonic flaw detection, we also need working curves to reveal the mystery of workpiece quality. Next, let's learn the relevant knowledge of common ultrasonic flaw detection curves and reveal their meanings. Firstly, ultrasonic flaw detection curves mainly include two types, namely AVG curve and distance amplitude curve. There are many used for sensitivity adjustment and defect quantification of ultrasonic testing of forgings and welds respectively. Let's learn AVG curve first. First, what is AVG curve? AVG curve, which describes the relationship among the distance, echo height, and equivalent size of regular reflector. A, V, and G are the abbreviations of distance, gain, and size in German. Its English abbreviation is DGS. The significance of drawing AVG curve is to quantify the defects in the workpiece and select the detection sensitivity. The quantification here refers to the measurement of the reflection equivalent of the defect. The deflection sensitivity is a benchmark sensitivity of defect detection, which can ensure that the reflected wave height of the specified equivalent size defect within the detection depth range reaches the specified height. In the process of use, AVG curves can be classified in many ways, such as general AVG curves and practical AVG curves according to the generality of use. According to the waveform used to draw AVG, it can be divided into P-wave AVG curve and S-wave AVG curve. According to the different reflectors, it can be divided into flat bottom hole AVG curve and horizontal hole AVG curve, etc. The following takes the AVG curve of flat bottom hole for P-wave detection was an example to explain its drawing method. General AVG curve and its making. In order to be applicable to a probe of different specifications, the distance between the regular reflector and the sound resource and the equivalent size of the defect are normalized. The so-called normalization is a way to simplify the calculation. That is, the dimensionless expression is transformed into a dimensionless expression and becomes a scalar. The normalization process here is to divide the ultrasonic sound path by the length of the near-field area of the probe to obtain the normalized distance, which is the abscissa value of the general AVG culture. The dB difference between the echo height of the large flat bottom and the height of the initial wave, and the dB difference between the echo height of the flat bottom hole and the height of the initial wave are taken as the ordinate values. The normalized defect equivalent G is obtained by dividing the flat bottom hole diameter dF by the probe wafer diameter d0 as the characteristic value of each curve in the general AVG curve. The calculation formula and drawn general AVG curve has shown in the figure, as we all can see here. The curve B is the figure, is the relationship curve between the height and the distance of the large flat bottom egg. Except for curve B, other curves are the relationship between the egg height and distance of flat bottom hole with different values. It should be noted that when drawing the general AVG curve, it can only rely on theoretical formula to calculate and draw the curve in this area, as you can see when x is more than 3m. For the area within 3m, since the theoretical formula is no longer applicable, the curve of this area needs to be obtained through actual measurement. Practical AVG curve and its making. The practical AVG curve can be obtained by changing the abscissors in the general AVG curve to the actual ultrasonic sound path and the value to the actual size of the flat bottom hole. Therefore, the abscissors of the practical AVG curve is the actual sound path and the ordinate is the dB value. The practical AVG curve is measured and calculated by the specific probe, so it is only applicable to the specific probe and has no generality. It is necessary to mark the probe specifications on the drawing. In the process of drawing the curve, when flaw detection is carried out on regular reflectors with different sound paths, it is necessary to find the highest reflection peak position of the flat bottom hole by moving the probe on the test block. Then adjust it to the proposed reference wave height, such as 80%, and finally record the ultrasonic sound path and the dB value reading of each reflector. In another case, in daily flaw detection, in order to quantify defects more conveniently and quickly, we can draw AVG curves directly on the instrument oscillograph panel, which is called Pano AVG curves. This kind of curve can only be used on instruments with good vertical nonlinearity and a positive relationship between wave height and sound pressure. Different from the practical AVG curve, the drawing characteristics of the Pano AVG curve are that the abscissa is the horizontal scale of the panel, representing the ultrasonic sound path. The ordinate is the percentage of the vertical amplitude of the panel, and the characteristic value of the curve is the diameter of the flat bottom hole. And all data points used in drawing the curve are obtained through actual measurements. Let's learn the distance amplitude curve again. What is a distance amplitude curve? The range amplitude curve is a curve that describes the egg height of a regular reflector change with distance. It belongs to the category of AVG curves, and any curve in the AVG curve clusters belongs to range amplitude curve. It is mainly used for sensitivity selection and defect quantification of S-wave angle probe flaw detection. There are usually two ways to express the range amplitude curve. One is to use the amplitude dB value, which takes the dB value, then with the echo height reaches a certain specified reference height as the ordinate and the distance as the opposite to make the curve, which is conventionally called the range dB curve. The other is a curve whose amplitude is expressed by the percentage of the screen height, which is the ordinate and distance is the opposite. In actual testing, it is made on the flaw detector display screen, which is called the Pano distance amplitude curve. The distance amplitude curve can be obtained from the actual measurement of the test block or the theoretical calculation formula. Similarly, the latter is only applicable to the case where the ultrasonic sound path is, as we can see here. However, In actual production, the thickness of the weld is often less than that. Therefore, the distance amplitude curve for weld flaw detection is generally measured on the test block. According to the relevant standards, the distance amplitude curve can be obtained by CSK-IIA or CSK-IIIA test blocks. The drawing method of the range amplitude curve is basically the same as that of the AVG curve described above, except that the transverse hole is used as a regular reflector. Next, let's learn how to draw the practical distance amplitude curve. Use CSK-IIIA test block to draw distance amplitude curve. Since the primary wave method and the secondary wave method need to be used to detect defects in the flaw detection process, the flaw detection shall be carried out at least within the depth range of 0 to 2t. Therefore, the distance amplitude curve shall be drawn based on the test data of the least 5 short transverse holes within the depth range of 0 to 2t. The specific steps are as follows. Place the probe on the CSK-IIIA test block and detect the depth of 10 mm on the test block by 1 mm times 6 mm short transverse hole. Adjust the instrument to make its echo height reach the reference wave height, and record the hole depth and attenuate reading at this time. Then repeat the previous step to detect another depth, short transverse holes, and obtain each group of measurement data. Take the hole depth as the abscissa and the dB value reading as the ordinate. Establish a coordinate system on the coordinate paper and trace points based on the measured data. And finally, collect them into a smooth curve that is obtained, as we can see here, this amplitude curve from 6 mm short transverse hole. According to the provisions of non-destructive testing standard MBT 47003.3205, the evaluation line EL, quantitative line, rejection line, and all this distance amplitude curve position relationship of 6 mm short transverse hole. By planning up and down phi 1m, draw above the 3 lines with the distance amplitude curve of 6 mm short transverse hole. From the above description, we can know that the complete distance amplitude curve is composed of 3 lines and 3 regions: the evaluate line, the quantitative line, and the rejection line. The area between the evaluation line and the quantitative line is called zone 1. The area between the quantitative line and the rejection line is called zone 2. And the rejection line and the above regions are called zone 3. So far, the distance amplitude curve is drawn. Finally, the drawing of Pano distance amplitude curve is briefly introduced. Its drawing steps are similar to Pano AVG curves, except that when phi, as we can see here, after the drawing of the short transverse hole curve is completed, the sensitivity needs to be improved through the attenuator according to the table lookup information to convert the curve into an evaluation line. Okay, that's all for this class. See you next time.